Right.
Okay, so welcome back. We have the pleasure to have with us Paolo Salucci, who will tell us about the new paradigm and scenarios for the dark matter phenomenon. So, thank you.
Okay. First of all, can you hear me perfectly? Okay, it's problem. And first of all, I want to thank the organizer for this, I see more than 1 week of organization on the frontier from neutrinos. And you will see, it seems that my talk will be quite different from other talks because it is not centered in neutrinos, but centered on other things. But you will see that at the end, there will be a surprise for which neutrinos, they will come out. Okay, so first of all, the title of this is Paradigm Scenario for the Dark Matter Phenomenon. So the first thing to do is to tell that this talk, what is this talk? This talk is to say, to convey a proposal that is a new way to approach the dark matter mystery. And this way is motivated by the observational properties that have emerged in the past 20 years. So I will immediately write down or tell you what is the result of this talk, is that given the dark matter phenomenon that we know today, it's very likely that we need, if we want to have the true scenario for the dark matter, to adopt also, to change also the generating paradigm. Okay, this is the result that we will discuss about this during this talk. And one important thing is that in this talk, I will really say, put forward a lot of results and plots and so on. But still, the discussion is not on those results, but on how do you interpret this result. If one wants to have a very, very, let's say, deep understanding of all results that I will show, then there are other papers and which one can really understand better what's going on. The point is not on the result, because this result have been used hundreds of times in the past 20 years. So really the point is, how do you interpret this result? We will be clearly in a few minutes. First of all, dark matter. Dark matter, it is not a particle. So the point is dark matter is a phenomenon. It's a phenomenon that emerges at any scale from the expansion of the universe. Okay. Sorry, this one. From the expansion of the universe to the CMB, to the kinematics of galaxies, to the bullet clusters, the DAO, the existence itself of galaxies, the strong and weak lensing. So there are a lot of astrophysics, say, results, astrophysics evidences that can be explained only if there is, say, a particle which is invisible but acts gravitationally. Okay, so this is, let's say, the phenomenon of dark matter. Another important aspect is that the phenomenon, to get the scenario that will explain this phenomenon, scientists have have resorted to a paradigm. Okay, you start with the phenomenon, and you assume a sort of paradigm, and then you get this, which, for instance, explain what is the dark particle. So then is the true, or the accepted theoretical scenario emerges out a paradigm. So since 1990, the paradigm that was, say, around or beyond the dark matter was called the Apollonian. What it means? Means that the true scenario for the dark matter particle has to be the most beautiful possible. What does mean beautiful? In this sense, it connects dark matter physics, new dark matter physics, with known physics of the universe, shed lights on open issues of the standard model, or even some other long-standing big issue of physics. It has unique particle, which is detectable by experimental observation with near future technology. And the dark matter particle is introduced in a natural, simple way, and is related to the cosmological matter density. Mathematically, is described by a very small number of parameters. It has a unique known initial conditions. It has strong predictive power and in the evolution of the structure, and importantly, can fully followed by suitable numerical simulations. So beauty means simplicity, means naturalness, usefulness, achieving expectations, harmonically extending our knowledge. This is something which, for instance, works very well with GR or with many other aspects of physics. And the people thought that could be the crucial point, the crucial paradigm to get the dark matter. And in effect, this appears because from this paradigm, a specific scenario emerged. There was the collisionless WIMP dark particle or dark matter. This, just to say, you know, this is fully falsifiable by observation, experiment, theoretical argument. And what important, when it came out, it has also another enormous advantage, that is automatically reproduce all formation, all the dark matter, the phenomenon of dark matter present in the time in which it put forward. Reverse engineering, then it's set. I don't know. Can you hear me? Okay. So I continue this. Okay. So it's set to reproduce. Okay, it is set to reproduce automatically any dark matter phenomenon that will be in year to come. Okay, then this particle, these advantages is clear, and it is, just to give an example of this success, is that we have more than 35,000 papers on galaxy formation and so on, based on this theory. And you know, on the other side, that at the moment, they have not been found the particle, for instance. But still, this theory, this scenario, has so strong basis that continues to be, let's say, the most important one. Now, one important aspect of this scenario is that the n-body simulation have enormous, let's say, advantages. So in this case, in this scenario, basically, you have only that halos within halos within halos. All what the universe produces is halos that interact by themselves gravitationally and form galaxies and then cluster of galaxies and so on, in a hierarchical way. So it is very, very simple, say, but extremely powerful way to describe what happened in the universe. This is a characteristic that is on this scenario, and is not obvious because just the other kind of scenarios, they don't have this simplicity and even the possibility to have simulations that they are, say, explaining what's going on in the universe. So, and one important aspect is that, as I said, halos within halos within halos, they have all the same profile. That is this. This is extremely important. Also because 25 years, the first, say in 1996, people found the all object in the universe. They had this density profile. 25 years later, they found again that this structure goes from moon-size halos out to superclusters. So really, one has that the universe in this scenario form by balls. No? Okay, in this. Now we go to really not the simulation, not the theory, but observations. Galaxies, very important to say, the galaxy, they come in families. So there are different galaxies, at least as far as the luminous component. One has the ellipticals, they are sphere, until you go to the laser fast blindness, they are disk, very, very giant disk, and so on. They are all kind of different, let's say, profile. And of course, the point is that each of them, because all these families has a lot of very values in luminosity and in mass, so you have basically a number of objects that they can be, each of them, a laboratory. Okay, so it is clear that there are families. Okay, so but this family includes also the luminosity. But it's true that it's not true that every galaxy is the same, is different. So it's not that every galaxy is the same, but it's not also that every galaxy is different. Then if you put yourself in, let's say, between 100 and 1,000 galaxies, are enough to explain the, let's say, the whole, let's say, universe. But certainly needs several hundreds of galaxies to do so. Then what is important is that the distribution of stars, or I don't want to enter in astrophysics too much, but what is interesting is that there is a size, no, of the galaxy, okay, of the luminous part of the galaxy, and there is also luminosity, no, that is the number of stars in this galaxy. These are the only thing that they say needs. The distribution of the stars is very similar in all objects. Okay, there is but of course they have a size and they have a luminosity, a mass. But the distribution is the same. If in elliptical, for instance, all elliptic have this kind of distribution. This is the surface brightness of the star. It is the surface brightness on spiral galaxies. So then how it goes? So then from the gravitational potential, you get mass distribution. Mass means all mass, no? Luminous plus dark matter. And then you have the gravitational potential, the Poisson equation. And then you have another equation, depending if your system is rotating, is pressure dominated, or you get this from weak lensing, or from X-ray emitting gas. So there are methods that they get the gravitational potential, and then you, when everything is correct, you can decompose your component, your mass, in two components, one luminous and one, let's say, dark. When one does this, and it is important to say that, first of all, the galaxy mass model, I say one component that is dark, one component that is baryon, then only 3 free parameters and 1 free function is sufficient to do so. So then the parameters are simply one, the stellar mass, okay, that is not known, or if you have any method to get the stellar mass from the luminosity, so this is not even a free parameter. And then you have 2 parameters that you choose in the dark matter halo. So the dark matter halo has a function which is free, and this function has to have 2 parameters which change galaxy by galaxy. This is enough. Any model with simple luminous component that uses more is overfitting the data. Any model that uses less parameter than this one is very unlikely that can fit the observational data. Then the dark matter. What is the dark matter? Dark matter, okay, in the paradigm that I decide, the scenario that I decide, the dark matter halo has this profile. Okay, so, and it's interesting that you have a cusp at the inner part, and outside it goes like minus 0.2.5, minus 0.2.6. This, and then it comes at the end of the galaxy. From observation, I introduced that you have a core, so in the sense that they are flat, okay, in the center. It is as two effects. First of all, they are different clearly from the NFW profile, but they come out with these two free parameters that they don't exist in this scenario. Okay, because the center in this one is infinite, so R0 should be 0, and R0 infinite. So this is something which do not exist in this scenario. It's not only that it's different, simply do not exist, does not exist. So you have a mass modeling of data. I showed just a flash out on different kind of galaxy, different type of galaxy from, for instance, this is the biggest galaxy of the universe, M87, the local universe, to dwarf elliptica, they are very small. Not always the result is perfect because there are more difficulties sometimes less, but what comes is that the structural parameter, they come related. So then you have, for instance, here, the central density, ρ0, the core radius, R0, and the disk mass. They are related. So even more, you can see here, this goes for spiral, core radius, helocentral density, fraction of dark matter, and luminosity. So you see that they are mixed together, quantity that they are on the dark matter, and quantity that they are on the luminous matter component. Okay, so this is just, say, could be that this is something due to galaxy formation. So then, if in effect, for instance, in the feedback, for instance, baryonic feedback could create the core. We will see this. And as far as there is not an explanation on this in this Apollonian paradigm, but we want to test this fact with better, with more, useful data. And so, okay, so what we get? We get that the dark matter not only is flat, this is the density of dark matter as function of radius and mass for all the for spiral galaxy, for instance. The blue one is the observed. When you go in the outer part, because this is the radius goes in this way. When you go in the other part, you see that the observation, they are similar to the prediction in the, let's say, collisionless scenario. So the point is in the internal part. In the internal part, there is this discrepancy. And this discrepancy, let's say, in a certain point, disappears when you go in the outer part of the galaxy. So then one say that there is something going on in the innermost part, there is a sort of interaction, okay? But at the outer part, there is no time enough that this interaction has taken place. And so you have the original, let's say, distribution of matter. Because one could say that in time scale of 10 to 8 years, that is the time scale that it is sufficient to form galaxies, then it's very unlikely that the dark matter could be interactive, okay? Because the time scale is very, very short. And so it is quite interesting. So as for instance, the clusters, in the outer part of the clusters, the dark matter is, let's say, collisionless, but because really they have not have time to develop even some collision, even if the dark matter is collision dominated. So then we have that this is quite important because not necessarily this should be useful, okay? In the sense that the other kind of dark matter, they will not have these properties. So one property is that the dark matter must converge more or less to the collisionless state when you go outside. Okay, in the inner part is completely different thing. Okay, one important aspect is that the effect is only 2 or 3% in the mass. So this discrepancy that is giant because it is the discrepancy in the luminous part. So outside the luminous part, there is no discrepancy, but we don't have a luminous matter to sometimes to realize this. When we realize this, there is enormous discrepancy. Okay, then we come to the first. So the first is that the relation between the central halo density and the core radius. So we have in each galaxy a region of constant density, this is the radius of this region, and the value of the central constant density. And this one goes from M87, which is the biggest galaxy, which is about 100 kiloparsec, to the smallest galaxy. Of course, there are a lot of, let's say, scatter clearly, but you have such relation. So when you come a new profile of dark matter, this comes with these two free parameters that they are related. This is important because it's not so obvious that you can do, even if you go out from the, let's say, collisionless dark matter. For instance, axion, phasor, Bose and psi condensate, they have a relation which goes in that direction. Okay, at least these models in the simplest, let's say, situation. Then, if you do something more complex in this, with this particle, maybe you can do this. But at the beginning, you have this, which is, let's say, almost, let's say, as bad as cold dark matter, which cold dark matter is stay here, and should stay in this region. So then this is the first relation. And the second, which is even more incredible, is that the stellar disk versus the core radius of the halo. So you have a properties due to obtained by the stellar distribution with the properties due to the dark matter halo. And this goes, let's say, from, let's say, a small 20 parsec out to 100 kiloparsec, and in different kind of object. They are very, very different, because just to say, each of these objects has a different mass, has a different fraction of dark matter, and a different also morphology. But this relation between these two quantities remain the same. And it's clear that if you don't have a sort of relation like this, if you have two components that are luminous or interactive, it's obvious. Okay, so if you go in for instance, giant molecular clouds or so, this is a relation which appears quite strongly if the two components, okay, the components in which you may tease the component, the two components are both interacting. If they don't have, you have not, you need to have a no adiabatic exchange of force momentum. In the moment in which you don't have this, okay, it's very difficult to think how you can do, you can say, obtain such relationship. Another, I will say, is the compactness. Compactness means how much compact is the stellar disk, how much compact it is the halo. Okay, so this one. And the two things are completely different, because the compactness of the disk of the luminous part is due to the formation of the stellar disk, and the compactness with the halo is, we don't know what is. The initial conditions, we don't know how this can come. But certainly in the first approximation, one doesn't remain that these are different. They are related. What we find in different galaxies, by the way, they are the most different kind of galaxy they could be. The laser fast blindness, so the giant galaxy, and then we have the smallest galaxies, the smallest size galaxy, and you find that there is a relation 1 by 1. So they more concentrated is dark matter, more concentrated is the luminous matter. So the two things, they are okay to explain, and mean if they come out, but there should be a direct interaction about this. And this is important, because when if you have from baryonic feedback, you will have a relation between the two things, but we'll go in the other direction. So in the sense that more you are compact, the luminous matter, and more effect you have in the luminous matter, so in the dark matter. So because if baryons supernova explodes, and then the supernova makes, let's say, the cores of the galaxy, so then the more explosion of supernova there are, and more and less dense is the dark matter, let's say, in the inner parts. So it should go in this way. So this is another way for which halos, the core radius of the halos are not really made by baryonic feedback, at least not only by baryonic feedback. So then one has also another thing that when you go at high redshift, you have the core radii of the galaxy for the same mass, they are smaller a factor 2. This is the result that is important, means that the evolution, you have a sort of evolution of this core radius situation, okay? And then this is the core radius at redshift for the same, for galaxy of the same mass. This is the core radius at redshift 0, and this is the correction al redshift 1. You have a core, but is, let's say, factor 2 smaller, and the density is higher. So it seems, okay, again, that it is this kind of destroying, no, dark matter. So in the innermost part, there is starting of removing or destroying or absorbing dark matter in the innermost part and on large time scale. So the time scale is the time of the universe. And even on this is supported by this one. So you have, this is the radius of the core radius, okay? So then in this inner part, say one has issues because doesn't have collisionless profile. The density in this part, the fraction of the product of the two density, they are equal in all objects. So it seems that if you have, there is something universal that gives a rho square values, that if the product about the 2T quantities is larger than this, you have, let's say, a profile which is not collisionless. You get the collisionless profile when the product of this is smaller than a certain quantity. And this is quite important, nice, because you see in galaxies, this quantity changes a lot, okay? 6 order of magnitude is more. And instead, when this goes within a factor 2, and this defines perfectly, let's say, the region where is the end, okay, of the current distribution, so the end in which you have something going on over, we say, the scale of the time of the universe. Okay, so then come down, these are some, say, no, they are not all, but I had to reduce for my time here. These are some of the phenomenon that is the dark matter phenomenon in 2023, for instance. The most important aspect is that this is very, very different from the dark matter phenomenon in 1990. So I repeat that one of the great advantages of the lambda CDM model is that it is sufficient because to explain the dark matter phenomenon at any kind of things. But this is also a, let's say, a problem, because anything that comes out in the universe, which is different from what the people thought in 1990, cannot be easily accommodated, okay? So then what we have a emergency, the strong entanglement. There are inconsistencies on scale, they are small. So this disagreement is so deep that why we say, this is related to the paradigm rather than to the particle, okay? Because the paradigm, for instance, forbids the dark matter also this kind of scenario to evolve in a different way. Okay, so the failure of this scenario, okay, start now. We have many philosophers. The last one is Nietzsche, which put, let's say, in crisis this idea that beauty has to be truth and false has to be ugly. So the idea that a scenario with a lot of free parameters, with a lot of, let's say, ad hoc, let's say, it has to be rejected. Maybe, as far as the dark matter concerned, is not maybe necessary, is not useful. So then we start to say, to change the paradigm that allows new kind of scenarios. So then the scenario has to be with the new paradigm, the scenario has to be agnostic with respect to the scientific beauty, okay? Has to, let's say, allow scenario that appears ad hoc, anti-hoccam. I would say that even in these seminars, some people, they said, okay, this is favored by Occam. So not necessarily to be Occam favored is a good thing. And especially they maybe do not scenario that don't make any progress in the open issues of physics. Actually, they could put other issues to the physics. So, and it is iteratively reversing engineering the dark matter phenomenon as this place with time without leaving possibility that this can evolve, okay? So now with the new JVST data, we will go to have, for instance, galaxy always a black hole, so initial black hole always had very near to the Big Bang. So has to be not completely closed that any new result is against, you know? And what important thing is this paradigm is only to apply for the dark matter, no? So not for any other things, including the dark energy, although they have, the people in the dark energy arrived to similar conclusion. But we are putting that just to make progress now, we have now to change paradigm, because if it's not clear that you are changing the paradigm, even if you use another scenario, but you still go and try to get, let's say, the beauty, you, let's say, you make yourself a very bad case, because you don't have all the advantages that lambda CDM has, and again, you are against, you are say within the paradigm, which is very, very limiting. So really, we have to discuss this, because automatically people, otherwise they will go towards to the, let's say, to the Apollonian scenario. So the paradigm shift is this one. So the Apollonian, so you start, as far as the dark matter, you start from the first principle or theoretical background. You find that in 1990, there was a crucial moment in the history of physics in which, as far as for the dark matter, the first principle and the dark matter phenomenon was really one reverse engineering of the other. So then, dark matter, and you can have you can get at the end the observation or detection. So the new paradigm instead start from, let's say, the dark matter observation, a galactic, also any other case, and it result in a sort of back and down from the scenario and the observation. It is built, okay, as far new data comes. So then it is a sort of reverse engineering between the dark matter observation, dark matter scenario, and also first principle when they come in. So there is not really a particularly important, because we can go in that direction and go in the other direction. Then this could help the dark matter detection, but the dark matter detection can be looked at also independently. So you can try to get to try also blind detection in, okay, not completely blind, but in certain, I mean, almost blinded attempt to detect the dark matter independently of you have understood the first principle of this dark matter. So this is the new paradigm, and it is important to discuss this, because otherwise you, even with scenario which are on this paradigm, they try to get to the other scenario. And doing so is even worse than, as I said, assuming from the start this scenario, because this scenario is really lambda CDM as in galaxy formation is by far the best. So, and there is no way that any other kind of particle can be even near to the success on, say, beauty on the lambda CDM scenario, in particular called the matter scenario. So, and now we go to the what is. So clearly, this is just to allow what. So then this relation, 2 minutes. Okay, I'll try to do. Okay, then this is a relation which goes to, let's say, the formation. So we want to have interaction between the two. And okay, so what is the direct dark matter interaction that can have dark matter standard matter particle interaction, and the multiple location interaction in stars, so on. And then I will go just to what the neutrinos are. So okay, so can be the dark matter, the degenerate 1 keV fermion neutrino, the QUIT plus self-interaction, which is not considered until now too bad. They can be the dark matter. You can find and solve some of the issues that I shown before. Then can help in push out the standard particle if the neutrino flux, for instance, for supernova and dark matter particle, they have in interaction, okay, that this maybe in a very complex way, this could solve many of the problems that I saw. It can be, let's say, witness of interaction between standard matter particle in stars. So then inside the stars can be in interaction, and neutrino can be the result of such interaction. So therefore, I don't know if some neutrino anomaly are just suggesting this, but in these 3 cases, neutrinos are important in going for the new scenario of dark matter. So then, okay, I think I stop here, saying that we have to start with scenario that they are more related to the data. We have to assume that the data are really, let's say, they are important and they're not automatically due to astrophysics, okay? And so this, let's say, I think is the way forward for the moment. And with this assumption, with this, let's say, strategy, we can get nearer to the dark matter that for the moment, okay, is very, very still keep to be mysterious. Okay. Grazie.
Thank you, Paolo. So time for discussion. Yeah.
You mentioned that you mentioned the dark matter distribution outside some certain level of like a how can I say, like outside the region of the galaxy remains as it was like from the initial condition. Then there should be some boundary values for that. Like what are those?
Can you?
Yeah, it's difficult to hear you.
All
Can
right.
you talk louder?
All right. So you mentioned that the outside galaxy's distribution of dark matter remains as it was, like from the initial condition, right?
Yes.
And then there should be some boundaries for that. For example, it can be like an 8 kiloparsec for our galaxy, or like it can be a 1 kiloparsec for, I don't know, dwarf sphere the galaxies.
Okay.
So I'm wondering if there are like any like measurements from Andromeda galaxies, which is kind of like a twin galaxy of our
Okay,
galaxy.
the information here is much less important than in the inner part, because we have the tracer of the gravitational field is due only for weak lensing, for instance, or other, let's say, very, let's say, complex thing with respect to the kinematics in inner part. But from what we can see for the moment, it seems that in the outer region, let's say from observations, you have a collisionless distribution. And on the other case, you see if you estimate the time of the free fall time or Faro interaction is really more than 1 gigayear. So it's not so strange. If you have a configuration of 1 megaparsec or 100 kiloparsec, in the outer part, any matter has no time to interact with other even if could interact. So it is not strange, the fact that it will be strange, for instance, if we will find a different, and then this will really be that Newtonian gravity is not anymore correct. So, because if you are in Newtonian gravity, you have to have the usual profile, independently of the dark matter, in the very, very outer region. But if you have, for instance, Mond, you will have a different profile velocity, and this will be, in some sense, important, but it's not. I don't know if.
So like my question is, what are those values for our galaxy? Like, so what is outer side of our galaxy? Is it like
Okay, the
beyond
region,
10 kiloparsecs?
the region important between the two differences is about the size of the galaxy, the luminous matter.
Just the size of the disk of galaxy.
Exactly. This is important because it seems that when there is not one or two component, nothing happens. When you have one component, something happens, but you need to be two components.
Right.
So this is, sorry, I couldn't.
Thank you.
Other questions? Comments? Ah, voilà. Okay. Yeah, Luis and then Sergio, or vice versa. It's up to you. Okay.
So let me see if I got that right. So you said that we should look for dark matter blindly without imposing or assuming that we know something, or because if we do it blindly, how do we search for it?
No, I'm talking about that. Looking blind, for instance, I don't know, some line, if there are some lines, or the X product in a galaxy, you have gamma ray or something like this, without really a model, no, around. This is not crazy. I'm not saying that we should look this, but this is not lazy in the meantime, because we don't have a scenario which will predict like this. But for instance, gamma rays, any gamma rays production coming from a galaxy, and or other things, then maybe could help us, and we can have some, just to say that we could have a proof of the existence of the dark particle without even looking at the dark particle. Instead, okay, for WIMPs, we know that they have to be in a particular, say, observational setup.
But I wouldn't call that blinding. I mean, you're actually looking for something and you're making a connection, which is not a blind connection.
Okay, we'll say, okay, by luck, okay, yes.
Okay, Luis.
So can you go back to your figure with the density versus the scale radius of all the galaxies? Do you have, yeah, it's like rho naught versus R naught, the core.
So sorry, I can't
Oh, well, actually, I can just ask. So you know which figure I'm referring to, right? The density. So do you have like low surface brightness galaxies on that? Yeah. I mean, I just have a question about these kinds of galaxies.
Which one? Which one?
I think it was the other one. No, it's the simpler one with the row versus. I can just ask the question. I don't need the figure actually. So I can just ask the question. So the brightness galaxies, you know, there's been a lot of work done on those, like past several years, and there's work done that the core size that you induce that you measure from the dark matter, like really depends upon like, sort of your viewing angles and various other geometric properties, which are considering in sense that like you could actually, you know, there's been simulations that have been done where it's like actually have a, you know, a Cuspi system in the galaxy or a core IS space, you know, and is this the error budget when you're measuring what the core density is in all these galaxies, or just a general comment you have on that?
This depends a lot some galaxies, for instance, the walls of galaxies, then this evidence is much the best. So is say in some sense have to be compared with the uncertainties on which you find this. In effect, I will put some kind of there about in the determination, and even the presence of say the code in some objects, say for instance, one galaxy, another kind of strange, the galaxy is has to be over 100%. But here I'm not, as I said, in the first paragraph that I got the review, which is quite going on, and there are 100 pages in which everything is saying. Now, today I want to change the paradigm. For the moment, it seems the paradigm that I would like to change makes all galaxies equal. So now there is time, don't really discuss the by one on one, but I think that there are even more complex things. And I will not that some galaxies maybe would not have the same cost. So this is I think.
Tiziano, you had a question, Tiziano? No? No? Comments? No. Other? No? Okay. If not, let us thank Paolo again.